Kia ora koutou. This is a question that Snehal sent in, and it's a really, really good example of the thing I went on and on about in class, which was checking whether you've got a linear combination of random variables or the sum of random variables. So the thing to think about in this question is how many different sources of variation have we got? And if you go back to basics, you'll get this question right. It's not that difficult if you just take it slowly. So we've got the weights of cups have a normal distribution with a mean of 91 grams and a standard deviation of 3.2 grams. The weights of sauces have an independent normal distribution with a mean of 72 grams and a standard deviation of 2.6 grams. Cups and sauces are picked at random to be put into boxes. There are 6 cups and sauces, 6 cups, 6 sauces in each box, and the empty box weighs 550 grams. So what we've got to do is build the distribution of weight in a box, because we have to figure out the probability that the total weight of a box of cups and sauces will exceed 1,550 grams. Okay, so first of all, just let's work out how can we describe the distribution of weight of a cup. Well, we'll call the cup C, and it's distributed normally, and the mean is 91 grams, and the variance is going to be 3.2 squared, right? So I'm working at the level of the variance, because when I add up variation stuff, I work with the sum of the variances, right? And the sauces are independently normally distributed. On average, a saucer weighs 72 grams, and the variance will be 2.6 squared. All right, so what about the weight of a box of 6 cups and saucers? Well, first of all, the box weighs 550 grams, no variation for that, so it's going to be 550, and then it's got cup 1 and cup 2 up to cup 6, and then it's got saucer 1 and up to saucer 6. So notice that I did not write this. It's not 550 plus 6C plus 6S, right? The way to think about this is if I took, suppose for some stupid reason that the weight of a cup affected its price and that you paid $6 per gram of weight, then that's what I would be working with, right? But that's not the situation we've got here, because we have got 6 separate cups and 6 separate saucers, and each of those has its own variation. So the expected value of a box of cups and saucers will be the 550 plus the expected weight of cup 1, and so on. So you can see that when I'm doing the expected value or the mean, I'm not going to run into trouble if I've made the mistake of thinking it's a linear combination, right? Because this is going to work out as 550 plus 91, blah, 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 91, and then that's going to be 72 out to 72. So this is the same as going 550 plus 6 times 91 plus 6 times 72, right? And that gets me an average weight of the box of cups and saucers of 1,528 grams. For the variance, if you go back to the chapter in the book that went through all the basics, we know that the variance of B, because everything is independent, is going to be the variance of all of this, which is equal to, or the variance of this is just 0. So this is equal to the variance of the first cup out to the 6th cup. Now, obviously, you don't have to write it out in this much detail in the exam, but if you have done a good setup on this question like this, you're much less likely to go wrong with it. So here, the variance of the box of cups and saucers is going to be 6 lots of the variance of 1 cup, so it'd be 6 times 3.2 squared, and then 6 lots of the variance of a saucer, right? 1 for each saucer. And that gives me, when I do that, 10.24 plus 6.76 times 6, which gives me 102. Now, all the hard work is done. All we've got to work out now is the probability that the weight of a box, I think I was working with B, not W, so probably that B is greater than 1,550. I'm not doing anything with continuity corrections in here because it's all measurement, so it's not something where we've had rounding happening. So the probability that Z is greater than this, I'm going to standardize as usual. I reckon most of the class at this point has hung up the video, but if anyone's out there still watching, we would get Z is greater than 2.178. So drawing our little picture, hang on, let me just turn off ink to shape. Ink to shape is really good, except when it's not really good. So we want this little area here 1 minus phi of 2.178. We wash up to our normal table. Here's 2.17 and our little add factor. So we've got 0.9853. So 1 minus all of that gives me, happily, the same answer that they've got in the mark schedule, which is 0.0147. So there you go, Snehal. Great question. I reckon probably most of the class could do with going over that. But hopefully that's cleared that up for you. Now, if anyone's still got problems with this concept, just send me in a couple more questions. But I've already videoed quite a lot of problems like this. So if you go to the A-Level Stats 2 playlist, you'll find a number of videos that are labelled linear combinations or sums of independent normal random variables. Thanks for watching. I'll do a couple more videos soon.